Welcome to Spring LIB.
So if A and B have the same cardinality, that means by definition that there's a bijective map that goes from A to B. Or it's one-to-one. Now let's define a function g that goes from the power set of A to the power set of B. That maps a subset S of A to the set f of S, which I recall is defined as the set of f of little a such that little a is in S. So it's the image of all the elements of the set S. We want to show that this G defines a bijection. And that will show that the cardinality of power set of A is equal to the cardinality of power set of B. So is G injective? So let's say that G of big X is equal to G of big Y. That means that by definition of G, the set containing all the images of the elements of big X is equal to the set of the images of all the elements of big Y. But now these two sets are equal. That means that for every X, there is a Y such that f of X is equal to f of Y. Because the first set contains all the images of little x, well, of all the possible little x's, and the second set contains the images of all the possible little y's. So there must be a bijection between these two sets. In particular, f of x is equal to f of y for some choice of x and y. But now f was bijective, so x must be equal to y. And this works for every element x and every element y in big X and big Y. So the set big X is equal to the set big Y, and therefore G is injective. Then is G surjective? So let's take a big set Z in power set of B. We want to find something in power set of A that gets mapped to Z. Now Z is a subset of B by definition of power set of B. Let's put X to be the counter image through F of Z. And I recall that this is by definition the set of the counter images of little z, where z ranges over set big Z. This set X lives inside A, and by construction, G of X is exactly Z, which shows that G is surjective. Therefore, G is both injective and surjective, which means it's a bijection.